Hello everyone! Today we will be discussing about operational amplifiers, commonly known also as op-amps, which are fundamental components in analog electronics, and these devices are used extensively in signal processing, filtering, and different kind of mathematical operations. My name is Sofia Barrera Torres and my partner Samuel David Sanchez and I will be speaking about this today. An operational amplifier is a high-gain electronic device that is designed to amplify voltage signals and is one of the most essential components in analog electronics, widely used as a signal conditioning, filtering, and mathematical operational component. Op-amps are versatile and can play a crucial role in many electronic circuits because they enable precise control and manipulation of signals. Something important are the stages of an op-amp. An op-amp consists of multiple internal stages that work together to ensure a high gain, a good stability, and also a signal integrity. I'm going to talk about the four important ones. The first one is the input stage. This stage creates a voltage difference between the inverting and the non-inverting terminals and amplifies that differential signal. As an example of differential amplifier is used to provide high input impedance, also minimizing signal loading and preserving the integrity of the input signal that was the original one. The second stage is the intermediate stage. This stage is further amplifies the signal that is received from the input stage. It operates with direct coupling, meaning that the DC voltage level is higher than ground potential, allowing it to have a smooth signal transition to the next stage. The next stage is the level shifting stage. Since the DC voltage from the intermediate stage may not be an optimal or perfect level, this stage adjusts the voltage to a more suitable range and it utilizes an emitter follower with a constant current course, ensuring power signal conditioning before reaching the output. And the number four is the output stage. This final stage increases the output voltage and current driving capacity of the op-amp. As an example, a push-pull amplifier is typically used to reduce distortion and improve efficiency, ensuring the op-amp can deliver a stable output signal to the next component of the total circuit. Now we can talk about the ideal and practical characteristics of or parameters in an op-amp. Now let's talk about the ideal versus practical characteristics or parameters in an op-amp. In an ideal scenario, an op-amp should have the following characteristics. The first one is an infinite open loop gain, meaning that it can amplify any signal without limitations. Also, an infinite input impedance, so it does not draw current from the input signal. The third one would be zero output impedance, this allowing maximum power transfer to the load. The other one would be infinite bandwidth, the infinite bandwidth, meaning it can amplify signal across all the frequencies. And the zero input offset voltage. This ensures that the output is exactly zero when both inputs are at the same exact voltage. However, in real world, the op-amps deviate from this ideal behavior due to manufacturing limitations. So we have the real ones. First, a finite open loop gain, meaning that the amplification is limited and it depends on the frequency of the op-amp. The second, that is high but not infinite input impedance, which still allows a minimal current draw but is not perfect. Then we have the low but not zero output impedance, which affects how the op-amp interacts with other connected components in the circuit. Another one would be the limited bandwidth, meaning that its performance decreases at higher frequencies. And finally, the non-zero input offset voltage, which can cause small but noticeable deviations in the output signal. But to compensate these practical limitations of the real world, the designers use different kind of components in the total circuit to compensate this. Another important thing to be explained is the distribution of the LM741 pins and what is the use of each one of them. So let's talk about the pin distribution of the LM741 amplifier. The first one is the pin 1, the offset null. This pin is used to adjust the input offset voltage, which is a small voltage difference between the inverting and non-inverting terminals that can cause like unwanted output deviations that I mentioned before. The second, the inverting input. This is one of the two differential input terminals. A signal applied to this pin will be amplified with a phase inversion at the output, meaning that a positive input results into a negative output when configured as an inverting amplifier. In other configurations, such as differential amplifiers, this pin receives part of the feedback signal. The pin number 3 is the non-inverting input. This terminal receives the input signal that is amplified but without the phase inversion. It's a non-inverting amplifier configuration. The input signal is applied to this pin and the output remains in the phase with the input. It is also used in differential amplifiers circuits where the voltage difference between pin 2 and pin 3 determines the output. The number 4 is the negative power supply. This pin is connected to the negative voltage supply. In a dual power supply configuration, it is commonly set to minus 15 volts, while in single supply circuit, it may be connected to ground. It provides the necessary power for the internal transistor stages that I mentioned of the op-amp to work. The pin number 5 is the offset null. This is similar to pin number 1. It's used for offset voltage adjustment when connected to a potentiometer, and it helps minimize any small differential voltage at the input terminals that could not affect the signal accuracy, but it usually is not connected. Then we have the pin 6, that is the output. This is the output terminal where the amplifier signals is generated. This output voltage depends on the configuration and the gain of the amplifier. The LM741 does not have a rail-to-rail output, meaning that it cannot reach exactly the maximal or minimal volt level, so it is slightly limited. The actual output voltage is influenced by the input signals and the feedback network that is used. Then we have the pin 7, that is positive power supply. This pin is connected to the positive voltage supply. Typically is is plus 15 voltage, and in a single supply configuration, it provides the necessary power for the internal amplification stages of the op-amp to work. And finally, we have the pin 8 that is not connected. This pin has no internal electrical connections within the LM741. It is presented in the package but does not serve any functional purposes. So in many cases, it's unconnected because it doesn't have any impact circuit performance. And understanding the function of each pin allowed us to understand the proper circuit function and to work in these applications that I mentioned before. So in this presentation, we will be exploring these key op-amps parameters in detail, discussing how they affect real-world circuit performance and how to optimize them for specific applications, because understanding these parameters can help us to make informed design choices. So let's get into it. Now let's get into the electrical characteristics or parameters of the LM741.
Okay, so first one, we have the input offset voltage. Imagine an ideal op-amp. The voltage at its inverting and non-inverting terminals should be exactly the same when no input signal is applied. In other words, if the input differential voltage is it's equal to 0 volts, the output should be also 0 volts. However, in real-world op-amps, due to small mismatch in internal transistors during manufacturing, there's always a slight voltage difference between the two terminal inputs. This small unwanted voltage is called input offset voltage. Why does this matter? Input offset voltage is amplified by the op-amp's gain, causing an error at the output voltage. In sensor applications, for example, this can lead to inaccuracies in measurements, as even a small offset can introduce a significant deviations in high-gain circuits. Typical values for these offsets for general commercial op-amps, input offset voltage range goes from 1 millivolt to 10 millivolt, and for precision op-amps, the offset can be reduced to the scale of microvolts using advanced manufacturing techniques like laser framing. How can we fix it? One way is offset null pins. Some op-amps include offset adjustment pins that allow us to fine-tune and reduce that offset using an external potentiometer. Another technique is auto zero, that precision op amps or chopper stabilized op amps continuously correct their own offset voltage internally. Another way is with calibration software, because in digital systems the error caused by that offset can be corrected by applying an offset correction factor. And finally, using a better op amp. High quality op amps with lower input offset voltage can minimize the problem, especially in high gain applications. Additionally, be aware that input offset voltage drifts over time and with temperature. So, if working in high precision applications, choosing an op amp with low temperature coefficient is crucial. Here we have a non-inverting amplifier configuration, and we can see that the gain, um, led by the resistances, it has to be multiplied by the input voltage plus the input offset voltage. So the offset voltage is also amplifying, and this value goes for the LM741. It's about typical value is at 1 millivolt of offset, and the maximum value is 5 millivolt at 25 degrees Celsius, or 6 millivolt. And here we can see how it affects AC signal by applying a DC level to it. Voltage. The supply voltage of an operational amplifier determines the range of voltages that the op-amp can handle at its input and output. It's conditioned almost every aspect of the op-amp's behavior, including input voltage range, output voltage swing, gain, and power consumption. If the supply voltage is too low, the op-amp may not function correctly, limiting the signal range and causing output distortion or clipping. On the other hand, exceeding the maximum rated supply voltage can damage internal components and permanently degrade performance. The choice between single supply or dual supply configurations also affects how signals are processed, with single supply requiring additional biasing to handle AC signals properly. These values for supply voltage for L11741 are the minimum are plus minus 10 volts. The recommended by the manufacturer is plus minus 15 volts, and the maximum is plus minus 22 volts. Now we're gonna talk about input bias current. In an ideal op-amp, no current should flow into the input terminals. However, in real op-amps, a small current is required to operate these input transistors. This current is called input bias current. Each input terminal, inverting and non-inverting, draws a tiny base current if the op-amp is BJT, or a gate leakage if it is FAT. This current is necessary for the transistors to function properly. Why does it matter? When the input signal is passed through high volume resistors, these bias currents can cause voltage drops, creating errors in the output voltage. This is particularly significant in high impedance sensor applications, where even a small bias current can cause large offsets. How can reduce input bias current errors? Use op-amps with low input bias currents like CMOS that have lowest bias currents compared to BJT based ones. Some precision op-amps have input bias currents as low as picoamperes. Or two, use buffer circuits like voltage followers. These values for of input bias current for LM741 at 25 degrees Celsius, the typical value is 80 nanoamperes and the maximum is 500 nanoamperes. Now we're going to talk about input offset current. Even if the input terminals are supposed to draw identical bias currents, in reality the bias currents at the inverting terminal and the bias current at the non-inverting terminal are slightly different due to transistor mismatches. The difference between these two bias currents is called the input offset current. Why does it matter? Offset current affects the circuit accuracy. If this input offset current is large, it introduces additional error voltage, especially in high impedance circuits, and it depends on temperature and aging. Like input offset current can drift over time and worsen at high temperatures, affecting long-term performance. How can we minimize input offset current errors? Choose op amps with low input offset current. Some precision op amps have this characteristic in the picoamperes range, or match impedance at both input terminals if the non-inverted input has a source resistance. Adding a matching resistor at the inverting input helps reduce errors. Or three, use a chopper stabilized op amps. Chopper op amps periodically correct their offset voltage, minimizing both input voltage current and input offset current automatically. These values of input offset current for the LM741 at 25 degrees Celsius, the typical is 20 nanoamperes and the maximum is 200 nanoamperes.
The input voltage range. The input voltage range of an operational amplifier defines the range of voltages that can be implied or applied to its input terminals without causing distortion or malfunction. In an ideal op-amp, there would be no limitation or of the input voltage, but in real devices, this range is constrained by the internal transistor circuitry and the power supply limits. The input voltage range is typically slightly lower than the supply voltage range. For example, if we have a plus minus 15 volts supply for the op-amp, the input voltage range may extend from approximately minus 14 volts to plus 14 volts, ensuring proper operation without saturation or clipping. If an input voltage exceeds this range, the op-amp may enter nonlinear operation, producing inaccurate or unexpected output. Some op-amps are designed to handle rail-to-rail input voltage ranges, meaning they can accept input voltages that extend all the way to the positive and negative power supply rails. These rail-to-rail input op-amps are especially used in low voltage circuits where maximizing the input signal range is super essential. Now, according to the test conditions of the LM741, we have an input voltage range with values of a minimum plus minus 12 volts and a typical plus minus 13 volts. The large signal voltage gain of an operational amplifier refers to the ratio of output voltage change to input voltage change when the op-amp is operating with large signal variations. It defines how effectively the operational amplifier can amplify an input signal over a wide output voltage range, typically spanning from near the negative power rail to the positive power rail. In an ideal op-amp, this gain would be infinite, meaning any small differential input voltage would result in a significant output voltage swing. However, in real life op-amps, the large signal voltage gain is finite and is typically expressed in volts per millivolts or decibels. High performance op-amps can achieve gains of 100,000 decibels or more, ensuring that even small input signals are amplified accurately. Now, according to the test conditions for the LM7041, we have a large signal voltage gain with a minimum value of 50 and 25 volts per millivolts and a typical 200 volts per millivolts.
Output voltage swing. The output voltage swing of an operational amplifier refers to the range of voltages that the output can reach before hitting its limits. Ideally, an op-amp should be able to swing from the negative power rail to the positive power rail. However, in real-world op-amps, the output voltage swing is likely less than the supply voltage due to internal transistor saturations and voltage drops. For a standard op-amp, the output voltage typically swings from about 1 to 2 away from the supply rails. For example, if an op-amp is powered by plus minus 15 volts, the actual output swing might be around plus minus 13 volts, meaning it cannot fully reach the power supply rails. Certain op-amps called rail-to-rail output op-amps are specifically designed to maximize this output range, allowing the voltage to reach close to both supply rails, often in the range of the millivolts. These are particularly useful in low voltage applications, such as battery power circuits or precise analog digital converter interfaces, where maximizing the dynamical range is critical. For the LM741, these values at a voltage supply of plus minus 15 volts and a load resistor of bigger than 10 kilo ohms, the minimum value is plus minus 12 volts, and the typical is plus minus 14 volts. And for a load resistor of bigger than 2 kilo ohms is plus minus 10 volts minimum, and typical of plus minus 13 volts. Now with LT Spice, we measured the output voltage swing of 11741. As we can see, it's a comparator. At its inverting terminal, we have ground. At its not inverting terminal, we have a signal of 1 volt amplitude and 60 hertz. The supplies are plus minus 15 volts. So the out voltage, the output should ideally should go to plus 15 and minus 15. But as we can see in the graph, it not reaches it, but 14 and minus 14 volts, as the manufacturer said in his datasheet. The output short circuit current. The output short circuit current of an operational amplifier refers to the maximum current that the op-amp can supply when its output is directly short to ground or one of the power supply rails. This parameter is important in determining the current driving capability of an op-amp and its protection mechanisms against excessive current draw. In normal operation, an op-amp is designed to drive a specific log of resistance, and its output current is typically limited by internal circuitry. However, if the output is accidentally short to ground or a supply rail, the op-amp will attempt to deliver as much current as possible, which can lead to overheating, damage, and long-term degradation. Most modern op-amps include short-circuit protections, which limits the output current to a safe level. For example, an op-amp may have a short-circuit current of limit of 20 to 50 milliamperes, preventing excessive power dissipation and protecting both the device and external components. However, continuous operation at its limit can still cause thermal stress and should be avoided. The output short circuit current is influenced by temperature and supply voltage. At higher temperatures, the op-amp internal protection may further be reduced the current limit to prevent excessive heating. Similarly, with higher supply voltage, the available short circuit current may increase, leading to a greater power dissipation. For applications where high output current is required, such as in power amplifiers of driving low impedance loads, it is important to check the op-amp's short circuit current and ensure it can safely handle the expected loads. If necessary, external current limiting resistors or buffer circuits can be used to prevent damage and improve overall circuit reliability. So for the LM741, the typical value of this maximum current that the amplifier can provide is 25 milliamperes. And in LT-Spice, we simulate that with this 10 ohm resistance to see to measure the current that flows through it, and we can see the value here of 0.025 amperes, and that is 25 milliamperes. So as the manufacturer said, that's the value. Now we have common mode rejection radio, CMRR. The common mode rejection radio is a key performance metric of an operational amplifier that measures its ability to reject common mode signals. That is, signals that appear integral at both the inverting and non-inverting inputs. Ideally, an op-amp should only amplify the difference between these two inputs, the differential signal, and completely ignore any signal that is common to both. In real-world op-amps, however, imperfections in the internal transistor design cause a small portion of the common mode signal to be amplified, leading to unwanted noise or errors in the output. The CMRR quantifies how well the op-amp suppresses this unwanted signal, and it's typically expressed in decibels. A higher CMRR indicates better performance, meaning the op-amp is more effective at rejecting interferences and noise that might be picked up equally on both inputs. A typical CMRR value for commercial op-amps ranges from 60 decibels to 120 decibels, while high-precision op-amps can exceed 140 decibels. For the LM741, that minimum value in decibels is 80 and the typical is 95. Now we're gonna measure that common mode rejection radio in LT Spice using the LM741. We're gonna calculate it. So we're using the differential amplifier configuration and we're gonna use purely differential signals and purely common signals to measure this. So for the common mode gain, we use two signals of 1 volt of amplitude that are equal, and we graph the V out. So the output shows voltage pike to pike of 132.58 microvolts. So now for the differential gain, we change the second source and the first one has still the same 1 voltage amplitude, but the second one also have that 1 voltage amplitude, but the signal is inverted, so they add up and we measure this output and we have a voltage pike to pike of 7.99 volts. Now that we measure the outputs, the differential inputs, and common mode inputs, we can calculate the differential gain and the common mode gain. And the radio between these two, we can find the CMRR, and we have a result of 30,131.8 of CMRR, which is when we do the conversion to decibels, we have a 89.58 decibels, which coincides with what was reported by the manufacturer.
Now, what is the supply voltage rejection radio? The supply voltage rejection radio is VRR, also known as power supply rejection radio (PSRR), is a key parameter that describes how well an operational amplifier can reject variations in the power supply voltage and prevent them from affecting the output signal. In an ideal op-amp, fluctuations in the supply voltage should have no impact on the output. However, in the real world op-amps, they have small variations in their internal circuitry that allow some portion of the power supply noise to couple into the output, causing unwanted signal deviations. Now, according to the test conditions of the LM741, we have a supply voltage rejection radio with values of minimal value 86 decibels and typical value 96 decibels.
Now the supply current. The supply current of an operational amplifier is the current draw from the power supply to operate its internal circuitry. It varies depending on the op-amp type, supply voltage, and load conditions. BJT-based op-amps typically consume more current than CMOs or GFA-based op-amps, which are optimized for low power applications. Higher supply voltages and driving low impedance loads can increase current consumption, affecting power efficiency and thermal management. In battery powered devices, minimizing supply current extends battery life and reduces heat dissipation. To optimize power usage, it's essential to choose low power op amps, use efficient circuit designs, and implement proper power management techniques. This value for the 11741, the typical is 1.7 milliamperes and the maximum is 2.8 milliamperes. Now we're gonna go with power consumption. Power consumption in an operational amplifier refers to the amount of electrical power it used during operation, typically measured in milliwatts or microwatts. It depends on the supply voltage and the current drawn by the op amp. Low power op amps, such as CMOS based designs, consume only a few microwatts, making them ideal for battery power applications. In contrast, high performance op amps using audio systems or instrumentation may consume hundreds of milliwatts or more. Excessive power consumption can cause heat buildup, reducing efficiency and reliability. To optimize power usage, it is important to select low power op amps, design efficient circuits, and use power saving techniques to extend battery life and enhance performance. These values of power consumption for the LM741 at a voltage supply of plus minus 15 volts. The typicals are at 25 Celsius, 50 milliwatts, and the maximum of 85 milliwatts. And the lowest typical is 45 milliwatts, and the maximum is 100 milliwatts. Now, the operating temperature. The operating temperature defines the temperature range in which the op-amp performs reliably. Temperature variations can affect critical parameters such as input offset voltage, bias current, and gain stability. High temperatures increase leakage currents and can cause thermal drift, leading to inaccurate signal processing, while very low temperatures may affect transistor switching speeds and overall responsiveness. If an op-amp is used in extreme environments without proper thermal management, it may exhibit performance degradation, unexpected behavior, and or even failure. Selecting an op-amp with suitable temperature rating ensures stability in demanding applications such as industrial, automotive, and aerospace systems. These values for 11741 and 11741A, the minimum temperature is minus 55 Celsius and the maximum is 125 degrees Celsius. For the 11741C, the minimum is 0 degrees Celsius and the maximum is 70 degrees Celsius.